So to this point, what we've done is we've established, hopefully, a framework of relevancy and, to a certain degree, what the responses would look like. It's linear, the relationship between VO2 and workload, and that to be more economical, one would have a lower oxygen cost for doing the same volume of work. So now we get to, okay, we've got a clear rationale for this, and hopefully you kind of get the sense of why this is so important. How do we go about assessing this? Now, in order to be able to understand how we assess this, we need to actually understand about the VO2 response to constant load exercise. Now, this will actually appear in another one of these classes. It's entirely up to you whether you want to jump forward to it, which is on oxygen uptake kinetics. But in the meantime, we'll give you a brief synopsis and perhaps a little reflection on what we mean. So we're going to use a paper published in the early 2000s. I think this is a woefully overlooked paper because it's so telling in terms of what this data shows us. So what Bernard has done is they've taken individuals, and this is basically one individual's data. This is average data. And what they've done is they've asked them to exercise at a range of different running speeds. And they've then recorded the VO2 response. In this case, they've recorded it in mils per minute. And they've done this at speeds going up by half a kilometre an hour. These will be on separate visits and separate trials. But what we see is we see that the response does not look uniform. Now, if we look at what happens at 16 kilometres an hour, then what happens at 16 kilometres an hour probably conforms with what our understanding is of the VO2 response to constant load exercise. I would hazard a guess that most people watching this would assume that it takes around about 2 to 4 minutes to reach steady state. And that's conventionally what is conveyed. That is the notion that the amount of oxygen being delivered to the tissue to meet the energy demand, to get that balance, takes about 2 to 4 minutes. And in fact, if we look at this data set here, at 16 kilometres an hour, that is exactly what we see. If you follow the trace up, notice the VO2 is rising despite the fact it's constant load exercise. Why? Well, it's rising because there has been a square wave transition in the ATP turnover rate. So there's been an instantaneous increase in the ATP turnover rate of the tissue to be able to run that speed. But the delivery of oxygen has a delay-like component to it. There has to be an acceleration in cardiac output. There has to be an increase in heart rate. We have to get a gradual increase in the amount of oxygen being extracted from the muscle, and so on and so forth. So the net result is we get this delayed response. So the VO2 rises gradually to meet the demand of the tissue, and then by 4 minutes, 240 seconds, we've reached steady state. And we've got steady state because there is no change in the VO2 response. In fact, you can see the trend line sits perfectly between the data points, indicating in this 840 second, in fact it's closer to 960 second bout of exercise, that actually the steady state was achieved at 4 minutes. But now look what happens to this athlete at 16.5 kilometres an hour, all the way up to 17.5 kilometres an hour. Something unusual happens, particularly if you look at the 16.5 kilometre an hour one. Notice, one, faster running speed, higher oxygen cost compared to 16 kilometres an hour. So that's in agreement with the definition of Barnes and Kidling. It's in agreement with what we saw in terms of the schematics from Saunders and Jones and so on. But they do not reach steady state in 4 minutes. So here's steady state in 4 minutes at 16 kilometres an hour, but notice at 16.5 the VO2 starts to reach steady state, perhaps slightly sooner, perhaps actually at around about, this is about 180 seconds, around 3 minutes in. And it looks like it's reaching a steady state, but it's not. What we get is a sudden acceleration in the VO2 response. And in fact, we don't really get to steady state until we get close to probably 360, probably more likely to be in the region here of well, closer perhaps to, so probably in the region of about 420 seconds, it starts to level out again. So we're not reaching steady state in the conventional 4 minutes. And there is a reason why that occurs, and I'm not going to jump forward in terms of the understanding, but again, if you're desperate to find out, go and watch the session on oxygen uptake kinetics. But just for the moment, understand this notion that we do not always reach steady state in a window of 2 to 4 minutes. Same when we go to 17 kilometers an hour, we've got this ever increasing O2 deficit. Remember, we're borrowing oxygen to meet the demand, and it only now starts to probably level out in the region here, fairly similar, 480 seconds, maybe up to about 480, 640 maybe, 600 seconds, 540 seconds, in that region there where it starts to level out. So there's clearly a different response happening at 16 kilometers an hour to what is happening in these speeds here. But notice what happens when we go up to 18, 18 and a half, 19, 19 and a half kilometers an hour, and even at 20. Notice that what happens is there's a higher oxygen cost because these are faster running speeds. But notice that a steady state, neither a traditional steady state that we see at 16 or this alternate steady state that we see from 16 to 16 and a half to 17 and a half, neither of those occur. And in fact, what we see happening is the VO2 rises inextricably. It carries on rising until we hit the point of volitional exhaustion, which is VO2 max. So we have three distinct responses. We have steady state in about 2 to 4 minutes. We have steady state in around about 5 to 8 minutes, which is this zone here. And we have a zone where we never reach steady state because the VO2 just keeps rising up to VO2 max. And these are defined as moderate, heavy and severe exercise domains. Again, more in the O2 kinetics lecture. So moderate is where we get a steady state in about 2 to 4 minutes. Heavy is where it takes longer. It looks like we're going to get a steady state, then it eventually is applied in around about 5 to 8 minutes. And then severe is where there is no steady state at all and VO2 rises to the point of volitional exhaustion at VO2 max. So this is very, very important to our understanding. So why do we need to understand this? Well, it tells us straight away, if we're going to assess economy in an athlete, two things we need to do. One, we need to get economy scores across a range of exercise intensities. And that would be exercise intensities that reflect certainly moderate and heavy, but not severe. So ask yourself, why wouldn't it be severe? Why would we not choose to record economy in the severe domain? Maybe just pause this a moment so you can have a little think. Okay, if you thought about it, I hope that your answer comes in fairly similar to what I'm about to say, which is, in order to assess somebody's economy, remember that what the quote from Barnes and Kildling was, it was, you have to be in a steady state. There has to be a point where the supply of oxygen meets the demand for energy at the tissue, at the muscle tissue. But if we're in the severe domain, which is, as we can see in this example here, 18 kilometers an hour upwards, VO2 never reaches steady state, it just rises to max. So you can't get a steady state VO2 response. So you would never record economy in the severe exercise domain. But it tells us then that we can't also do what is conventionally suggested, which is it's conventionally referred to, well, if you want to assess economy, 3 to 4 minutes, because somebody reaches steady state in 3 to 4 minutes. But we can clearly see that is not the case. They reach steady state in 3 to 4 minutes in the moderate domain, but when we go into heavy, as we've already iterated, you're looking in the region of 5 to 8 minutes to do this. So we have to account for this, what is called a VO2 slow component. Here's the VO2 level rising to a steady state, and then we accelerate, and this little area underneath this curve here is called the VO2 slow component. Again, we'll explain more in the O2 kinetics session. But it means that we have to take that into account when assessing economy. If we went just for 4 minutes, notice how we'd underestimate the VO2 response. So if we stopped the test at 4 minutes, in this example it's 16.5 kilometers an hour, so we would have got a value of 3,000 mils per minute, okay? Whereas actually, had we allowed the individual to reach steady state in 6 minutes, we'd be in the region of around about, sorry, 3,008 here, we'd be in the region of about, what, 4,000 mils per minute, maybe just slightly under that. So we'd have undercooked the relationship. We'd have actually made them look more economical than they actually are. So we know, just from this simple schematic, that we need to do economy trials across a range of intensities, but can't include severe, and that the exercise time for each of these trials needs to be longer than 3 to 4 minutes, and really, ideally, up to about 8 minutes. And if you're doing 8 minutes in these heavy, you might as well just do 8 minutes in the moderate, because notice what happens, it just remains stable. So it makes it much easier to kind of maintain that. And if we go to this from Glenn Gazer and Dave Paul, this was published in the late 90s, but it kind of helps explain what we've just been referring to. I'm just going to highlight all the key text for us. Oops. And they state this: despite considerable evidence to the contrary, it is common dogma that exercise oxygen uptake increases as a linear function of work rate to the maximum level. In reality, however, the linearity of the VO2 work rate relationship pertains only for exercise tests performed exclusively below the lactate threshold, or where the work rate is incremented rapidly to the maximum. Thus, for all constant load exercise tests which incur a sustained lactic acidosis, i.e. greater than the lactate threshold, a slowly developing component of the VO2 kinetics is superimposed upon the rapid phase of VO2, initiated at exercise onset. The magnitude of this slow component increases with work rate above lactate threshold, and if it cannot be stabilised, will drive VO2 to its maximum and signal imminent fatigue. So they're telling us some really important things. Firstly, the relationship between VO2 and work rate is only linear truly linear, up to the lactate threshold that they're referring to here, which you may have heard as the lactate turn point. And when we go beyond that point, we get this ever expanding VO2 slow component, and if we go way beyond it, we move from heavy to severe, then the VO2 never reaches steady state. And this schematic, just again, this is from Zhu and Rhodes, is quite useful. You can just see what's going on. Here's the onset of exercise. So you imagine the energy cost has gone up instantaneously to whatever it is. The VO2 rises, it's kind of a bi-exponential response, and it eventually reaches steady state. In the heavy domain, much bigger deficit at the onset of exercise. It looks like it's starting to level out, and then it accelerates again and eventually reaches steady state. And we're reaching steady state, as you can see here. In this example here, it's around about 5 minutes, maybe closer to 6 minutes. In the severe domain, notice no steady state ever occurs. There's more and more anaerobic energy being borrowed. This is what the deficit represents. It's the borrowing of anaerobic energy until VO2 rises to its maximum value, which is the point of volition exhaustion at VO2 max. So it really does lend itself to our understanding about economy, that economy really can only be reliably assessed in the moderate and the heavy domains, but only in the heavy domain if the exercise duration for each trial is long enough to account for the VO2